hours to say some FH. FH means upper 3 dB frequency, upper cutoff frequency or upper 3 dB frequency. Then you multiply the gain, voltage gain, say VA multiplied by FH gives you the GBP. Here VA SO, because it is starting from source of the signal, and VA FH is the bandwidth. And for current gain also, this definition applies for also current gain. The current gain bandwidth product is current gain multiplied by the frequency. And you see that it is dependent on RL, which is load resistance at the output terminal, which is connected to the collector of the BJT, and RS is the source resistance. Source resistance means source is your VS, which is going to generate a very small signal like mic. Okay, so this value may be very small, maybe 50 ohm or 200 ohm, whatever is. So from this GBP, it is clear that GBP is proportional to RL and inversely proportional to RS. The same thing has been plotted in the next figure. See that. First, look at that x-axis is your RL in ohm. Y-axis here, this axis is your FH, means upper cutoff frequency versus RL. As you can see that as the RL increases, FH decreases. That is one thing. Remember this diagram very carefully. Certain question will be asked here. So that is important. Then you see that gain bandwidth, this axis, gain bandwidth product GBP, how it is varying with RL. If RL is increased, GBP is this plot. RL is increased and GBP is increasing, as it was given in the here it is in the numerator RL. That is second point you are observing. And what about the effect of RS on GBP? As RS increases, what happens to GBP? RS is source resistance. Yes, Pratham?
So GBD also increases.
GBP will increase. Harsh Tripathi, when RS is increasing,
decreases.
Is it decreasing? See, for this at this point, remember GBP something where RS is 0. Okay, RS is 0, and GBP when 50 ohm. This is for 50 ohm. RS is decreased. RS is decreased. So this relationship you remember, and you could also see from here. It is in denominator. Anyway, remember this point because some question you may ask, expect from here. If you go through this, you will understand. Here FH has been plotted as a function of RL up to RL equals to, here it is 200 ohm or 2 kilo ohm. For several values of RS, several values means RS equals to 0, 50 ohm, 100 ohm, 250 ohm and infinite. The topmost FH curve in this figure for RS equals to 0 corresponds to ideal voltage source drive. Means if RS equals to 0, VS is your source, and RS equals to 0, that means it is a ideal voltage source. It is having no internal resistance. The voltage gain ranges from 0 at RL equals to 0 to 90 point. See, this one, this table is given here, 0 to 90.9 at RL equals to 200 ohm. Note that a source impedance of only 100 ohm reduces the bandwidth by a factor of about 1.8. The bottom curve has RS equals to infinite, corresponding to the ideal current source. Yes, if current source you are utilizing at the input of the amplifier, then the infinite current source resistance is good. Okay. It will be ideal current source. The voltage gain is 0 for all RL if RS is infinite. So voltage gain bandwidth product increases with increasing RL. Remember this. And decreases with increasing RS. Okay, that is good enough to remember, and you might be taking this snapshot, you read yourself. Now, few things we have not covered because I am covering only those topics which are mentioned in the syllabus. But these definitions are required for further discussion. That's why I have brought it without further discussion. I mean, in detailed discussion is required, but from the book, I think you have the book, so read from the book that these are the relationship which have been described there. We are just going to use this relationship, not going to derive at this point of time, otherwise I'll be lagging. So what the relationship is said here, we have just now discussed in the last class the RB prime, RBB and CE. These can be expressed in terms of H parameter also, like RB prime is HFE by GM. Okay, and RBB prime equals to HIE minus RB prime E. Okay, similarly CE can be expressed as GM by twice pi FT. So these relations I have just brought it for you, but its derivation etc. are given in other modules or sorry chapters of this book. We are not going to discuss that, then otherwise will be late. The high frequency response of a transistor amplifier is obtained in terms of the transistor parameters GM, RB prime, RBB, CE and CC. We shall now show that these may be obtained from the 4 H parameters. This FT is a transition frequency or unity gain frequency of a device. I mean, once you make a unity current gain, if you want to use it as a current gain, the unity current gain frequency is FT. Okay, 0 dB gain is going to give you the FT. Then HIE and HFE we have discussed, CO and COB we know. So from the operating current IC, which is a bias current of the BJT, and the temperature T, the transconductance GM can be derived as mod of IC by VT, where VT is what? Yes, anybody? VT is thermal voltage. It is not threshold voltage, it is thermal voltage. It is 26 millivolt. 26 millivolt it is, okay, at room temperature. So anyway, this definition we have to remember. We could discuss, but it will take long time to cover that portion. So I have taken the results or gist itself. Okay, if RS RL are given, the quantities in equation 113741 are known. we have therefore verified the frequency response may be determined from the 4 parameters. Hence, these 4 are usually specified by manufacturing company of the device, means BJT. Now we'll start discussion of emitter follower at high frequencies. So far we have discussed what? This up to this point we have discussed CE stage for low frequency response and high frequency response, followed by gain bandwidth product. Okay, of that C stage. Now we are going to discuss the emitter follower at high frequencies. We know what is emitter follower. We have come across. It's what how do you say that it is emitter follower? It is not C amplifier. What is the difference? Anybody?
Sir, RL.
RL is connected to emitter instead of collector. Isn't it? That is the main. You can look the circuit and tell yes, it is not emitter follower. It is not emitter common emitter. It is emitter follower. Anyway, and what is the gain? What is the gain of this circuit? Emitter follower?
Approximately 1.
Approximately 1, closer to 1. Not exactly, but closer to 1. Okay. So this all we have understood previously. Now we'll see how it is going to react at high frequencies. That's the topic here. Okay. And shown in this diagram, a capacitance CL. See, the CL is included across the load because the emitter follower, due to its low output resistance, is often used to drive the capacitive loads. Okay. So reason also mentioned why CL is taken. Now, see this figure at the bottom. Okay, it is for small signal analysis. This to be grounded. So this side is ground. Okay, and you have the emitter and other side. This is emitter. This is base prime. Okay, the internal point of contact of base is not actually leg of the transistor. So looking at this and using the KCL as we have done earlier, nodal equations can be written as this kind of equation we have already seen in the last class. Okay, so these equations can be written as we have done earlier, and GS prime can be written as 1 upon RS plus RBB prime, and G equals to GM plus GB prime. If BI prime is eliminated from these equations, the voltage BE by BS as function of AS is obtained. The result of the form given in this equation has 1, 0 and 2 poles. That is also discussed in the last class. If gain equation is coming in this form, then 1, 0 and 2 poles are there that we have discussed. Now we can obtain a very simple approximation or approximate expression for this transfer function if we apply the Miller's theorem. See, Miller's theorem if we apply here for this resistance and for this capacitance, you can split it and write this CE. This is a CE for your better visibility. This can be written as CE into 1 minus K, where K is defined as the gain from this point to this point. Okay, BE is here and BI prime is here. This is the BI prime between these two node, B prime and C. Okay, so similarly, resistance part, this part can be written as this. This is 1 upon this is the G. Okay, GB prime. Yesterday we have seen that. Okay, similarly, other part will be written here. I mean, not this one. This one and this one. Okay. So if you have a floating resistance and capacitance, then we can split into two part, and one part will be connected to one node and with the ground. This is the ground node, and another with this node and the ground. That can be done. The Miller theorem says this thing to do. Its proof we'll be discussing sometimes later in the other time. The single pole solution, for that, the low frequency gain of an emitter follower is close to unity, that is known to us. That is k equals to almost 1, and 1 minus k obviously will be closer to 0. Hence, the input time constant Ti will be what? Rs RBB into C. What is meaning here? See, this can be avoided. Okay, these two things can be avoided for approximation. Okay, because 1 minus k is going to be 0 because gain is almost 1. So these two things is neglected. Obviously, it is going to be approximate calculation. So time constant Ti is nothing but the summation of this resistance multiplied by Cc. Yes, Rc time constant is like this only. Yes or no? Tau is
Yes,
Rc.
sir.
The same thing is written here. Nothing new for us. We have also seen earlier, and you may be knowing also. Rc time constant is resistance multiplied by capacitance. And why it is neglected, that is also known to you. Because of the expression 1 minus k, 1 minus 1 is 0 almost, because k is closer to 0. So this is what you got the input time constant. The output time constant To is proportional to Cl, the Cl at the output side. Hence, the apath 3 dB, and since we have assumed that the load is slightly capacitive, then To much greater than Ti. Okay. Hence, the upper 3 dB frequency is determined to a good approximation by the output circuit alone using k equals to 1. Okay. So Be can be written like this. Be, this is the admittance. RL is here. Monopole RL is conductance, and another part is J omega Cl corresponding to this one. Conductance is what? Admittance, you can say J omega Cl or not. So this two, if you add and multiply, gives you this current or not. This current means this current. Is it understood? By manipulation, you can write k equals to this k0 by 1 plus jf by fh, where fh is the upper cutoff frequency, 3 dB cutoff frequency. So k0, where k0 may be approximated as 1 because GMRL will be much greater than 1, so it is almost 1. And fh can be written as ft by ftce by cl. Yes, relationship what we have seen earlier is written here. ft, see, we have already denoted here. Yeah, ce equals to what? This is taken. Ce equals to GM by twice pi ft. From here you can write that equation. Okay, you'll be getting this one, GM by pi, GM by pi will be equal to ft CE. Okay, and ft is given by this equation, and if fs equals to 1 upon twice pi tau 0, we see that tau 0 equals to CL by 1 upon GM, and the condition tau 0 much greater than Ti requires that CL should be much greater than GM multiplied by RS plus RBB prime into CC. So whatever value is this, here CL should be taken much larger than that here in the output. For the parameter values in this earlier figure, GM was taken as 50 milliampere per volt. This condition is CL should be greater than, putting this value in this equation, you get 23 pm, much greater than 20 pm. That means in this value, if you look at the figure number 11.14, every value means RS, GM, RVB, CC is mentioned. I'll show you the diagram. Yeah, this RS is mentioned here, RVB is mentioned here as 100 ohm, and CC is 3 PA, and CE is 100 PA. These all are given in this diagram. We are talking about that diagram and putting that CL's value, which was taken as this circuit emitter follower is normally going to drive a capacitive load. It was taken as CL. Okay, but CL's value should be what? Should be much greater than this 23 PA. From this estimation, it is coming. And since the input impedance between terminals B prime and C is very large compared with RS plus RBB, K also represents the overall voltage gain. FBS equals to VO by VS. Incidentally, a somewhat better approximation for FH is given as this. FH equals to GM plus GMB prime E divided by 2 pi CL plus CC. We can find the input admittance excluding RBB, excluding this one, by referring to this figure. Admittance YI prime, IB divided by VI prime. VI prime is between this node. It is given as J omega. It is admittance, so J omega is given. J omega CC plus 1 minus K, this one, CC 1 minus K CE plus 1 minus K CV. This is coming here. These all are conductances. So this is conductance because it is 1 upon RB there. So we get, so substituting the value of K was obtained here. Putting into this equation, we get YI prime as this. This much big equation we get. You put the value of K in this. Since K0 equals to 1, the numerator of this equation is affected by frequency at a much lower value of F. Then is the denominator. Hence, for F less than FH, this equation can be rewritten as this. this remaining same, this part of the equation remaining same, and here 1 minus K0 plus JF by FH remaining same from the denominator, since F is very small compared to, FH. See, FH is upper cutoff frequency, higher side of the mid-band frequency. So we can write this thing. It is going to be almost 1, this one. And which can be approximated as this. So what is the conclusion of this is, when the last term represents a negative resistance, this is a negative resistance which is a function of frequency. Obviously, F is there. Thus, the input impedance consists of a capacitance shunted by a negative resistance. This is input admittance we are talking about. So 1 upon that is the resistance, remember. So the input impedance consists of a capacitance shunted by a negative resistance. And if the source resistance Rs contains some inductance in series with it, it is possible for the circuit to sustain undesirable oscillations. Okay, since it is having a negative resistance which is shunted with a capacitance, and if there is a possibility of inductance, then it is going to oscillate. So at a higher frequency, some problem is going to occur. Okay. One way to remedy this condition is to use a small resistance in series with Rs. Okay, you would like to put a resistance in series so that these oscillations can be avoided. Now we are going to talk about, so far we are talking about the BJT based various kinds of amplifiers, and we have seen their low frequency as well as high frequency responses. Now we are going to talk about the MOSFET based amplifiers. One is called CS amplifier, which is called common source amplifier. Common source, CS means common source. Common source. And CD means common drain. Can you say which one is what? Corresponding to, which is correspond to which BJT amplifier it is? CS corresponds to what of BJT, and CD corresponds to what BJT? Yes. Okay, you will come to know during the discussion. Here is the low frequency small signal model of FET. See, MOSFET, you are aware of it, I hope. We have discussed sometimes in earlier courses. Yes or no?
Yes, sir.
So MOSFET, if you draw the symbol, this may be the N MOSFET, and this N MOSFET have various capacitances. So this is drain node, this is source, this is a gate node. Okay, and there is a body also. Okay, body terminal. So it is CGD, this is CGS, CGS, other capacitance, and between drain to body, CDB, CHB. Okay, another one is denoted between these two. CGB. Okay, so this is excluding the overlap capacitance. Certain capacitance are there, still I have not shown. So 5 capacitance you are seeing here, In addition to that, you have overlap capacitance as well as source and drain diffusion capacitances. I don't know this was discussed or not in the previous courses. Yes or no? Yes. Pratham, it was discussed.
No, sir.
Okay. Little structure I'm going to show you of an MOSFET. This is P-type substrate. P-type substrate means the silicon material which is doped with trivalent atom is the substrate. Trivalent atom means maybe what? And you want to make it P-type. What you will add? What impurity you will add to it so that it becomes a P-type? Can anybody say?
Group 3 element.
Such as?
Boron.
Good. So boron can be added to make it P-type. It has been doped and now it is P-type on which you can make directly N MOSFETs, right? So let us make this is N plus and this is P plus region. Sorry, N plus region. 2 N plus region. Over that silicon dioxide at the bottom. Then you have polysilicon. This one is polysilicon layer. Poly, and you have the gate. This is say source. This is say drain. Sorry, this is drain. Okay, and yes, body of N MOSFET is connected to. I was showing here in this say for the sake of discussion, you can put here at the bottom body terminal, which is normally grounded. Okay, and the source is also grounded. Okay, if a gate voltage is applied here, gate voltage, positive gate voltage in case of a MOSFET, then how it will happen? Positive charges will be deposited here, and those charges will be repelling the holes. It is having holes because it's P-type. So these holes will be repelled from this region, under the gate. Okay, so a depletion layer will be formed. A depletion layer will be formed here because also be repelled by the positive charges. But yes, if you increase the voltage little further, okay, increase the gate voltage, say VGS, gate to source voltage, you have increased a bit, then the more positive charge will be deposited at the polysilicon gate material, and what will happen? Electrical field will be strong. Once the electrical field is strong, then a layer of electrons will be lined up here in the channel region or in the under the gate silicon. This is silicon dioxide material. Remember, this bottom layer I have shown is SiO2 silicon dioxide material. On top of that, polysilicon material, poly-Si. So basically, it is a capacitor or not? It is denoted by COX, gate oxide capacitance. Okay. So this capacitor actually, when the MOSFET is in different region of operation may be one is cutoff region, other one is linear region, and third one is saturation region. MOSFET can be put into these three region operation. Gate voltage is 0. Instead of some positive voltage, say you have applied a 0 voltage, then there is no inversion layer or this layer of electrons, as you can show here, see here. The layer of electrons what has been gathered under the gate is not there, so current cannot flow from source to drain. I mean, electrons from source to drain and current from drain to source cannot flow in case of n MOSFET because gate voltage is 0, no inversion layer. It is called inversion layer. This layer is called inversion layer because basically it was P type substrate. Now it has been inverted into N type. As you can see, the channel region only is having this electrons. Of course, this electrons. Where from these electrons is come? Can anybody say? I have applied a positive gate voltage, so some electrons have been lined up there. Where from it has come? Any idea? No? Harshdeep, are you there?
Yes, sir.
Any idea?
Sir, maybe from the N channel, that N type material.
N type, N plus you are telling?
Yes, sir.
Sorry. See the N plus, let me say one thing. Okay, if you, I am again making something. So we have N plus, right? So let me say this side is N plus. Okay. And this is your substrate, P type. Okay. And this P type is connected to the negative terminal of the battery. Grounded means negative terminal of the battery. So tell me, negative terminal of the battery, and this is the positive terminal of the battery because here you have connected a positive voltage. Okay. Then only I was telling that yes, current will flow in this direction, electrons from source to drain in this direction. Okay. That was the situation I was telling. Drain side is having positive voltage, body is grounded, means negative terminal of the battery is connected there. So in that situation, tell me how electrons are available here. Can electrons, if you take it here, can electrons go from this side to here? I mean, pointing here. I'll take a red color. So you're telling that it may go from this N plus region to here. Or you may say that is, it may go from this. This is your point or not?
Yes, sir.
Is it possible? Is it possible for the electrons to move like this? Let me show this as N plus region. So in between you have the P type substrate, this portion. I mean, basically I am showing this portion. Okay, in this portion, let me take another color. I am actually showing this portion here in this diagram. Actually, we had electrons lined up here, which I call inversion layer. Inversion layer. So you're telling that electrons may be moving from N plus and N plus region. There is a PN junction here. One junction is here. Another junction is here. So tell me which junction is supplying these electrons, inversion layer electrons. If you are feeling that it is coming from this N plus regions, then which side is going from? On the left side N plus region or left side, right side N plus region? Yes, tell. Pratham?
The left side.
Okay. Why not then right from right side? Any question? Any guess? Any guess?
Sir, due to the electric field developed.
Due to the electric field, from right side it will not go. What is that electric field acting here?
Sir, the applied VGS.
So okay, say concentrate here in this junction. This junction, PN junction, is forward biased or reverse biased? Tell me. Yes,
Sir, reverse.
reverse biased. So reverse biased, can electron flow or current flow? Reverse biased because this negative terminal is connected here. Okay, positive terminal is this side. So electrons will be moving in this way. Here basically you have the, right now we don't have anything. You have the holes. Here a lot of electrons because it is N plus type. Are lightly doped, but still holes are there. So these holes will be attracted in this direction because it is reverse biased, and this electrons will be attracted in this direction. So can electrons go to this region? My question was how these electrons is coming. You said that is from the N plus region. Could you understand what I am meaning? I asked a question where from the inversion layer electrons are coming. You said that yes, it's coming from N plus region of the N MOSFETs. Drain or source diffusion region, that is called drain and source diffusion. One side is drain, other side is source. Diffusion regions, from diffusion regions it is moving. That is what your answer is. Now my question is it possible that it is moving? Harsh Tripathi, tell.
No, sir.
It is not possible because it is reverse biased. This junction is reverse biased. Now look at the left junction. Left junction means this junction is looked at. How it is biased? As I said, this left side N region is N plus region is grounded. So it is grounded, and body, which is also grounded. Okay, here I have shown this grounded. Okay, so both sides is grounded means no potential is applied between this junction. Am I correct?
Yes, sir.
Yes, sir.
Then will the electrons will come to here from this side. This side is having plenty of electrons, and other side is having holes. Correct? Because it is p type. This is n plus type. So now, then why? How? I mean, is it possible that electrons will be moving from right and left side to right side? No bias. Means you have a simple PN junction. One side is N type, one side is P type. Actually, it is N plus type. This is P type or P minus type. P minus indicates lightly doped. N plus indicates heavily doped with pentavalent atoms here. Phosphorus, for example. This is boron, as you said. Now, are you understanding my question? Hari bhai, what is my question? What I am asking? Aman?
Yes, sir.
What is my question? Are you listening?
Yes, sir.
Tell me, what is my question?
Sir, is it possible to that electrons from N side that is grounded will move to the P side?
Which is also grounded.
Yes, sir. But according to me, the N channel is formed from the P substrate only. When positive bias is applied at a gate, then holes will be repelled towards opposite side, and electrons which will be attracted towards the gate, and the N channel will be formed.
How electrons will be crossing? How electrons? There is a, see here, if there is no bias, what will happen? Tell me. You have lot of electrons this side and holes this side. Tell me what will happen at this junction, PN junction?
Diffusion.
Diffusion will, yes, diffusion will take place. Some electrons will go to the right side. Once it will go to right side, it will satisfy the vacancy left in the P side, and it will be a negative ion or positive ion. Tell.
Negative ion.
Negative ion. Left side, what will happen? It will leave behind a positive ion here.
Positive.
Okay? Positive ion means a depletion layer will be formed. In this, a depletion layer will be formed. Depletion layer will be formed here. That's it. And a voltage will be developed that is called built-in potential. Okay. Initially, the electrons will be moving in this direction. E will be moving in this direction, and hole will be moving in this direction. Okay. And they will form a depletion layer. Further, it cannot move because this side you have the positive ion layer. This side negative ion layer. Negative ion layer, right? So further, if it tries, suppose electron tries to move, then yes, it is going to face a wall of negative ion, and it will be repelled. So initially, it will move, diffuse to some extent, and a voltage will be developed. That is what is the voltage for SI? This built-in potential is how much?
0.7.
0.7 volt. Okay, you have understood and you have studied in electronic devices, I hope. So this 0. I mean, further, if it has to move to other side, it has to face a repulsion. It has to face a electrical field which is going to repel it. It cannot go. So how then electrons are going to, say, initially maybe there is a depletion layer around it. This side a negative ion, okay, negative ion, and this side positive ion. Am I correct or no? Very thin layer will be there. Now my question is, then how here you will get the electrons as I have shown here? Yes, could you get my question? Aman?
Yes, sir. Sir, the P substrate, in P substrate, the holes will be repelled, and
repelling is there, but
yes,
where from electrons is coming? That is my question.
Sir, the gate is positively charged. So, sir, the gate is.
Yes, tell.
Sir, the gate is positively charged, so there will be positive on polysilicon. So negative charge will be developed below that.
See that you are correct. You are correct. Whatever you are telling, whatever you are telling is correct. Suppose you are This is your gate material. You have connect gate. You have positive voltage you applied. This here you have deposited positive voltage connected. So deposited. Okay. Lot many positive charge here. Now my question is this side. Under this you have a depletion. Sorry, silicon dioxide here. Okay, and in this side you have N plus region. Okay, not here. Let me. N plus region. This side you have this right side. Also you have N plus region. Initially these holes, positive charges at the red portion. Red portion I'm telling it is a poly. Okay, polysilicon. So it has repelled. So repelling means holes are repelled means what is left behind? Tell me. Left behind will be what?
Electrons.
If holes are repelled, what will be left behind? Tell. Is a negative ion or positive ion?
Negative.
Negative ion. Okay. So due to repelling by the positive charges deposited at the poly, you have this kind of things. This has been depleted of positive charge carrier which are there in the substrate. It is depleted. I mean holes are pushed down. This is the situation when gate voltage is small. Okay, small gate voltage. VGS. This is source. This side is positive. So because of this VGS, this has happened. But you have increased the VGS further. So possibly, say, let me take another color. Say more charges have been deposited because of the higher gate voltage. So correspondingly, electrical field has increased. So what will happen? I said that yes. What will happen is electrons will be lined up here, which is called inversion layer. My question is, where from these electrons are coming? And we discussed that it cannot come from this side. It cannot also come from this side because right side it is reverse biased. This junction is reverse biased. Left side, this junction is unbiased because both the sides N plus as well as P substrate is applied with negative terminal of the battery. Both. I mean, there is no potential difference between that. Then my question still exists: how these electrons are lined up there? Is my question clear? Harsh Tripathi.
Yes, sir.
Is it clear? Question is clear or not?
Yes, sir.
Aman?
Yes, sir.
Is it clear? Question is clear.
Yes, sir.
We discussed a lot. From right side as well as from left side, electrons cannot come. Then where from it is coming? Do you think it can come? No? Yes or no? Based on the basic physics, we understand that yes, it cannot come from right side or left side. Then where from it has come? Yes, this has happened. This happens in the MOSFET or not? This kind of inversion layer happens or not? Have you studied earlier or not? Or have I explained in the last class, last semester? Yes, Mushraq Akhtar is missing nowadays. Just tell something, Pratham. Anyway, I am wasting time.
No idea, sir.
No idea. Okay. Did I discuss in little courses? No. No, yeah, yes. I think I discussed. What do you say? Are you remembering?
Sir, we discussed about drain diffusion capacitance. Sir.
Okay, not this one. Okay. Okay. So anyway, see, further courses will be there. In details we'll discuss. But for now, remember that any semiconducting material, whether it is p-type, n-type, or any semiconducting material, even at room temperature, always due to thermal agitation, electron hole pair gets generated. Do you know that or not? Thermally generated electron hole pair, you have heard about or not? Even at room temperature around 25 degree or 27 degree centigrade, always some electron hole pair getting generated, and of course it may die out also. I mean, it can recombine and vanish also, but keep on generating and keep on recombining. Okay, that happens always. So those electron hole pair, thermally generated electron hole pair, those electrons will be attracted by the strong electrical field at the gate, and they will land up here, and an inversion layer will be formed. Once this inversion layer is formed, now this, because of the inversion layer here, this channel becomes conductive. Now electrons from this side can move to right side, drain side, if you have a positive voltage here at the drain. Okay. So anyway, I'll delete all necessarily I have made. Now I have shown few capacitances, but I have also I should have also shown the drain diffusion capacitance, which I have already discussed earlier. Anyway, if I start discussing this way, then I'll not be able to go ahead. Let us discuss something else. ID, drain current of MOSFET, versus VDS. It is called output characteristics. Looks like what, you know? Yes or no?
Yes, sir. We know.
This is ID VDS plot. This is one plot, and another one is ID VGS plot. It is something like this. Okay. Ideally, this is the ideal case. Okay. Ideal means, otherwise you can say long-term MOSFET case. MOSFET. In long-term MOSFET, what will happen? When VDS is small, then ID will increase with VDS. After reaching some point, current will be constant. It will not vary with VDS. So this region is called linear region of the MOSFET, and here when current saturates, we call saturation region. Saturation region. So in saturation region, current ID doesn't depend on VDS. It becomes constant. With VDS, it doesn't vary. This is the case of long-term MOSFET. But channel length has been reduced a lot. Earlier it was say 5 to 20 micrometer micrometer was the channel length earlier. Now, say 20 micrometer means what, 20 micrometer is 20,000 nanometer. So 20,000 nanometer was the channel length. Channel length is what? Just now we have shown N plus region, then silicon dioxide. So this is your source, this is your drain. This length from here to here is channel length through which current flows. Current in this direction, electrons in this direction. This length is called channel length or gate length. Now, earlier this length was 20,000 nanometer. Now it is less than 20 nanometer. Okay, it has been L, which is less than 20 nanometer. Because of this characteristic has been changed. Now it is like this. With the VDS, current is increasing. This is not a desirable thing, but it is happening. In saturation also, current increases. So anyway, as you know, MOSFET is a voltage controlled current source. If you increase the gate voltage VGS, say I said here VGS, if you increase the VDS ID increases. So that voltage current source is denoted by this symbol GM VGS. VG is the gate voltage with respect to source. Okay, and because of this voltage source, MOSFET behaves like a current source, because if it is in a saturation region, current will be constant. If you take the constant current, then current source, ideal current source gives a constant current irrespective of the voltage across it. Voltage across it may be anything, but it will be giving the current source. Constant current. So that is what denoted by this GM-VGS. But yes, nowadays, today's MOSFET is also depending on VDS. So this behavior is captured by this resistance. Okay, means another voltage control current source could be written here instead of RD. Okay, that could be written as proportional to GM, say VDS. Is proportional to GM VDS. Okay. Means this current, another current source could be written which is the voltage VDS dependent. Now we know that current linearly increases in a resistance with the supply voltage. If you increase the supply voltage, current to a resistance increases. So that current source is denoted by RD. Okay, so without taking into capacitances into account, we have many capacitances. So for low signal analysis, you can represent MOSFET in this way. One is voltage current source, another one is RD. This RD is nothing because of the effect, short channel effect, which is called, if you extrapolate it, it will be touching the x-axis somewhere with minus VDS. Okay, some VDS will be here, and this is called early effect. Earlier in BJT is early effect. Now it is also early effect is called. Okay, you can check, but it's termed as channel length modulation. Modulation effect. Modulation effect. Okay. Why channel length modulation? Because if I can start discussing, then it will be like this: that current ID equals to 0 when VGS is less than VT. What is VT? Threshold voltage. Threshold voltage is the VT. Gate voltage is such that the inversion layer formed is negligible. It is not yet formed properly. If you increase the threshold, VGS greater than threshold voltage, then only inversion layer will be formed, and then current may be flowing if you are applying the VDS. So ID equals to 0 when VGS is less than VT. Second equation is ID equals to mu n C ox W by L into VGS minus VT into VDS minus VDS square by 2. This is linear region equation. And third equation is ID equals to mu n C ox W by L VGS minus VT whole square divided by 2. Okay, and remember this, for this also another condition. Condition for this one, let me write the condition with another color. This linear region condition is when VGS greater than VT and VDS less than VGS minus VT. Here it is when VGS greater than VT and VDS greater than equals to VGS minus VT. So these are the conditions for saturation region, because this equation is for saturation region and this is for linear region. So these three equations are I have written. The equation of MOSFET current equation. Yes. MOSFET current equation, three equations can be written. ID equals to 0 when VG is less than VT. ID equals to mu is W by L into VGS minus VT into VTS minus VDS square by 2 when VGS less than VT but VDS less than VGS minus VT. I mean, this is the condition for linear region. And for saturation region, condition is when VG is greater than VT and VDS greater than equals to VGS minus VT. And equation is ID equals to mu W by L into VGS by 2. VGS minus VT whole square by 2. Okay. So these equations will be required in future. These all not discussed here in your book. We'll be discussing in future sometimes later. But point was here that the small signal model of MOSFET is given here. The small signal model is represented simply by this one, figure A, without taking into account the capacitances. If you take into account the capacitances, then this capacitance has to be included into the model. Okay, because I have shown that there are 5 capacitances, excluding the capacitance, overlap capacitance, as well as drain diffusion and source diffusion capacitance. That is also not discussed. So based on this, we will go ahead for discussion of CS and CD amplifier. If you need further discussion, we can carry on much more in detail of MOSFET, but our course says that we have to understand this small signal model for this CS and CD amplifier. Once time is over, you tell me. I think time is gone. Yes, you are late. Yes, you are not telling anything. We'll be starting from here in the next class. Try to yes, sir. Try to read whatever earlier was discussed about the MOSFET, because the topic we are going to cover is about MOSFET, and that too high frequency response. And basically you are not knowing much about the MOSFET, so go through it a little bit so that you can understand next class. I could cover this portion, but could not go ahead without this. Anyway, tell whatever you are telling.
So we can give quiz on Monday 11:30 a.m.
Can you discuss with this section, other section also?
Okay, sir.
Because I want confirmation from both.
Okay, sir. We will discuss.
Discuss and WhatsApp me or call me and tell me, or mail me. Rather, you mail me. Okay,
sir. Yes, sir.
You have my email address.
Yes, sir. We have.
Okay, then do that. So that we have to take them into confidence. Okay. Otherwise, no, they will be